So for this example, we're given an elementary liquid phase reaction of A reacting with 2 moles of B in a reversible reaction forming 1 mole of product R. So the rate equation for this based on the stoichiometry is if it's expressed in terms of A, then it would be rate in terms of A being equal to 12.5 Ca times Cb raised to 2. So using the concentration of the species here, reacting species raised to their corresponding coefficients, this is your K sub 1, the rate constant for the forward reaction, minus that of the rate expression for the reverse reaction, which is K sub 2, in this case 1.5 times the concentration of product R, which is C sub R. Now, our unit is in mole per liter per minute. Now, if this rate expression is altered and expressed in terms of B, so now based on stoichiometry, the rate in terms of A is equal to the rate in terms of B divided by 2 because we have 2 here for the coefficient of B. Nonetheless, we still have the same rate expression on the right side of the equation because it's based both on the forward and the reverse reactions. Okay, so this one is for the forward reaction and this one is for the reverse reaction. Okay, now this is to take place in a 6-liter steady state mixed flow reactor. Now in this mixed flow reactor, you're given 2 feed streams, one containing 2.8 mole of A per liter and the other feed stream having 1.6 mole B per liter. So they are to be introduced at equal volumetric flow rates into your reactor. So you're not only having one feed stream, but you have 2 feed streams. Now, the conversion of the limiting component is 75%. This is the desired conversion for your limiting component. Now, there's this mention of the limiting component because you have 2 components. You have 2 separate streams. So you are to determine first which of the 2 components is limiting the production of your product R. What should be the flow rate of each stream in this case? So assume a system which is constant density. So if it's a constant density system and it's like that in most of the liquid phase reaction, your expansion factor or your fractional change in the volume is 0. Okay, in that case. So we'll get a picture of this and then we'll have the solution of this okay, determined. So this is for this part and our reactor is illustrated in this sense. So you have CaO, 2.8 mole A per liter. CbO is 1.6 mole B per liter. If you notice very closely, there's a prime in the concentrations. It's because when we talk of these two now, mixed together and reacting inside the reactor, this is not the corresponding concentration of the resulting mixture. This is just but the CaO prime and the CbO prime are just but the concentrations of each of the separate streams. Now, the volumetric flow rate, as mentioned, is equal for the 2 streams. So we have V sub A and V sub B, all small letters, is equal to V, since they are both the same, okay, or equal. The volume of your MFR is 6 liters, and it is so desired that you will have 75 conversion of B. So it was already stated here in my illustration that you will have 75% conversion of B, telling you that it was already predetermined in the illustration that your limiting component is really B. But we will first determine later on what is the limiting component. But nonetheless, this is correct. We are to determine the corresponding volumetric flow rates of these 2 separate streams, which are said to be equal, for us to be able to come up with 75% conversion of the limiting component B. Okay, so we'll go back to the key points later. We'll go back to our board. Okay, so this is our third sample problem. Your CaO prime is 2.8. We'll have another one. So CbO prime 1.6 mole B per liter. So this is A. We have a VA here, volumetric flow rate of that stream, and we have a VB, which is volumetric flow rate of this stream. These two being equal, let's say, will represent both a small letter V. Now the rate here is equal to, so we have 12.5 C sub A C sub B squared minus 1.5 C sub R. So the resulting unit here, units, is mole per liter per minute. Another thing that is given in the problem is the, of course, the stoichiometric equation. So you have A plus B. So this is 2 moles. So this is your K1, this is your K2, and forming product R. And of course, we have the product here. And what else? You have a 6-liter reactor. So the volume of your, why did I place 8? So this is 6. And what else? We have 75% conversion of limiting reagent or reactant. And the problem is requiring us to determine the V, the volumetric flow rate of each of the two separate streams. Okay, so I will read the problem again. That way you can recheck if there's anything that is not reflected on the given information. So the liquid phase reaction, liquid phase meaning we have to write right away that your fractional change in the volume, or rather your expansion factor, is 0. So you have that particular reaction written here, and the rate equation is also written here. The corresponding set of units is to take place in a 6-liter steady state mixed flow reactor with 2 feed streams, one containing 2.8 mole of A per liter and the other containing 1.6 mole B per liter. This is to be introduced at equal volumetric flow rates in the reactor, and 75% of the limiting component is desired. What should be the flow rate of each stream? Assume constant density throughout. So we have already accounted for such an assumption, and everything is already in here. Okay, now we will solve this as if we do not know the solution, or you're just starting to know how to solve chemical reactor design problems, that is. So what would you start writing here, or what should be the first thing that you should write in the first place? Suggestion, what should I write? I want the volumetric flow rate of each of the streams. I write the, of course, I need to write the performance equation. You may notice that we're so used to writing A, but this time we wrote B. We wrote B because even the rate was expressed in terms of B. It's because the problem is giving us a conversion that is based on component B. So you cannot write A here because the conversion that is given is that for B. Now this is the volume of the reactor, and this is the volumetric flow rate the volumetric flow rate total for the two separate streams already. So not just the volumetric flow rate of one stream, but rather the total volumetric flow rate. So I'd like to write here T. That way you can distinguish it from the small v that we have written in the given. The small v that I have written here is the same as the small v sub a and the small v sub b. But it's different than the V that is written here in the formula because this one considers the total volumetric flow rate of the streams that enters the MFR, not just of one stream. So this is V sub T. And I'm using component B here because the conversion that is stated is based on component B. So this is our working equation. Okay, now from this working equation, I'll get the V sub t, the small v sub t, to be equal to V times the rate in terms of B divided by CBO XB. Okay? I will know this if I know everything that I have in here. So far, based on what I have written, the only thing that I know for now is just this one, the V, the volume of the MFR. I don't even know the CBO because the CBO is not equal to the CBO prime that we have written. In the same way that CAO is not equal to CAO prime that we have written here in our illustration. You see there are primes here because these concentrations are based on the concentrations of these separate streams. But when we already determine whatever it is that is to be determined in a problem that has separate streams, you have to account for the real concentration of A and B in mixture form already, not in separate streams. These are the separate stream concentrations, and we want the mixture of these two as a whole already if these two separate streams are already mixed. So having said that, so I will make this as our first equation. Having said that, there's a need for you to determine the actual concentration in the mixture or in the final mixture of A and B, the separate phases, that the separate streams that is. In that way, you will have CBO being equal to your CBO is 1.6, your CAO is 2.8, all with primes. So if they are to be mixed with equal volume and you have 1 unit volume for A, then you also have 1 unit volume for B. Okay, so then the actual concentration of CBO in the mixture would be 1.6 divided by 2. Why? 1 unit for A, 1 unit of volumetric flow rate for A and 1 unit of volumetric flow rate for B. That would be 2 volumetric flow units for the mixture of A and B. So that is why we have already divided here by 2. So the actual concentration of B is not 1.6 in the mixture but only 0.8. So this is mole per liter. The same concept applies with that of A. So your A is 2.8. So you place here 2.8. We also divide by 2. So this would be 1.4 mole per liter as well. Now, since there is 75% conversion of the limiting component that is desired, you are to check which of these two is the limiting component. Now, you were taught in Chem 1, first year, on how to determine the limiting component. You go back to your stoichiometric equation. So the stoichiometric equation is this. So we are to check which of these two species limits the amount of R that is to be formed because R is your product. So we will do that now. That way you will know how to find the limiting component or the limiting reagent. Now, if we will use, so C sub R, if we will use all 0.8 moles of B per liter and you use the stoichiometric equation that is provided. So for B, 1 mole of R is formed for every 2 moles of B. So you have 1 mole R for every 2 moles of B. So we cancel this, giving you 0.4 moles of R per liter, formed if you have to use all of the B that is available. Now, if you will use A, so C sub R using A will be 1.4 moles of A per liter. Then you go back to your stoich. In here, you have 1:1. So 1 mole of R is formed for every 1 mole of A consumed. So you have here 1 mole R for every mole of A. So we cancel this, telling you that you will be forming 1.4 moles of R per liter for every mole of A that is consumed. So of the two, this is for B, this is for B, and this is for A. Of the two, the one that limits or produces the least amount of product is the limiting reagent. So therefore, since this is only 0.4 and this is 1.4, 1.4, so this is your limiting component or your limiting reagent. So it's B that you will use here because it's your limiting component. But before that, of course, you didn't know that it is B. So now I have placed in here that what you will use is CBOXB, not CAOXA, because the conversion of 75% that we will use, that you will be using, is that for the B component. So you will also determine separately the values of CBO. In this case, we have it already. I have solved it here already, and this is the value. So we will check this now as known. This is given in the problem. So what is next to be determined is the rate in terms of B. The rate in terms of B is all of this, except that you will transfer these two in here. So everything here will be multiplied by 2, your 12.5 and your 1.5. So let me just go to the next sheet. So for the rate in terms of B, that would be twice of the given values for the rate constant. So you have 12.5 and 1.5. So this is 12.5 CA CB squared minus 1.5 CR. Okay, so for us to be able to complete the rest of the variable in that particular equation 1, to be able to determine the volumetric flow rate of the two phases, there's a need for us to know everything that is written here. Now, this will be our equation 2. So in our equation 2, you need the C sub R, you need the C sub A, and you need the C sub B. Anyone who can tell me how will I solve for the C sub A? How will I solve for the C sub A, the remaining amount of A? Any suggestion? C sub A is, isn't it CAO minus CAOXA? This CAO was already solved, so we will determine CAOXA. Your CAOXA, I'll place here, your CAOXA, in terms of stoichiometric relationship in the provided chemical reaction. So this is our chemical reaction. 1 is equal to CBOXB over 2. Okay? So if you know the CBOXB, you will know CAOXA. So your CBOXB will be solved using the CBO that we have here, which is already 0.8. So this is 0.8 times the conversion, which is 0.75. We divide it by 2. So this is 6, or rather this is 0.6 divided by 2. So this would be 0.3. Kindly check my value. So you will have here a CAO Our CaO now is 1.4. So this is 1.4 minus 0.3. So your Ca is 1.1 mole per liter. You do the same with C sub B. Anyhow, C sub B is CbO 1 minus XB. Okay? Your CbO in this case is 0.8, and we multiply that to 1 minus 0.75 or 0.25, so that would be 0.2 mole per liter. So 1/4 of this is 0.2. Now I have the Ca already and the Cb that leaves the R. So for C sub R, that would be C sub RO plus C sub RO XR. This is the initial amount of R, and this is the amount of R produced out of the amount of the limiting component that has reacted. So we will base it on the limiting component. Now the problem is silent about R being present initially, so this could be 0. Okay, we don't have R initially present. So your C sub R is equal to C sub RO XR. And if I will continue here, in terms of stoic, it would be CRO XR over 1. So actually, this one and this one are just equal to this. So this is 0.3. Okay? CROXR is just over 1. This one is over 2. So same thing with CAOXA over 1. So this is 0.3. Now having all these three, you can now solve for the rate in terms of B. Can you please solve for it? The rate in terms of B. Okay. I will volunteer somebody. Okay, thank you, Sinoni. Okay. We have 0.2. So thank you, Jobern. So this is 0.2. Your R sub B. Since you have already that 0.2, so you can go back here and substitute everything. So from 1, so your V sub T, the volumetric flow rate total of the two streams will be computed now because we have everything already. So the volume is 6 and the B is or the negative R sub B is equal to 0.2 as provided by Jobern. So 6 and 0.2. Okay, and then that's the rate in terms of B, this one, the CBO XB. So your CBO XB, this is already 0.8 times 0.75, so that would be 0.6. So you have the total volumetric flow rate to be equal to so we have 2. So what's the volumetric flow rate of each of the streams? That would be 1. Because this one, so liter per, what's our time unit here? Minute. Okay. Do you have any questions? Okay, so 6. That's correct. Is this correct, the 0.2? Did you all check it to be 0.2? So this is the answer already. Do you have any questions? Okay, no more questions. We go back to our slide then. So this is our example 3. And from this example, we are able to design a mixed flow reactor, and that is determine the size and the operating conditions. So in here, we have determined the flow rates required to achieve a given objective. In this case, the given objective is the conversion of the limiting component. Now you're provided with the reaction stoichiometry and the reaction rate expression. Okay? So in this example, you learn how to determine the volumetric flow rate of the stream that was processed by your mixed flow reactor. So if you go to the third one, this one now is for a plug flow reactor. A plug flow, because you could see that now you have here as illustrated a cylindrical element of volume. Now, a gas phase reaction in this case, and you have A forming 3 moles of R. Now, the gaseous reaction occurred at 215 degrees Celsius, and its rate law is 0.01 Ca raised to 0.5 or 1 half with the units here mole per liter per second. You are to find the space time. So for this plug flow reactor, for 80% conversion of an 80% A, 80% inert feed to a plug flow reactor operating at 5 atm. So the temperature is stated, which is the operating temperature of your, or the temperature at which your reaction should also be occurring. You're also given the initial concentration of A, which is 0.0625 moles per liter, and you're given the illustration for your plug flow reactor here comparable to that of a cylinder or a tube. Now let's go to our board. So this is number 4. So we'll have a pipe here or a tube, a PFR. And for this PFR, you have 50% A here, 50% inerts. I'll just use I for inerts. And this is a reaction occurring at 215 degrees C and 1 atmospheric pressure. Oh, sorry, 5 atmospheric pressure. Your conversion, the conversion is 0.8. That's the conversion of A. Now, you have the rate expression or the rate law to be equal to 0.01 and Ca raised to 0.5 with this set of units, mole per liter per second. And the stoichiometric equation is A forming 3 moles of R. You are required to find the space-time. So the space-time is tau. Needed for 80% conversion. So I have already placed in here 80% conversion of a 50% A, 50% inert feed. Okay? So if we will start solving the problem, what should be the first step that we will be using? Um, what would be the first step that we'll be using? Epsilon A, correct. Extraction factor means. We'll use the expansion factor, may be what you mean, expansion factor, or we determine the epsilon A. Don't forget to start with this, especially if you're given a gaseous reaction. That way you will not forget. So this is our formula for the expansion factor. Now I need to determine the volume at 100% conversion. What would be the volume at 100% conversion? That would be the volume due to the inerts plus the volume. I place here 0.5 V sub O because we have 50% inerts, 50% A, 50% inerts. So our total volume after all of the A has been converted would be the 50 unreacted inerts. So that would be 0.5 V sub O plus the volume due to the formation of, in that case, that would be R, our product R. Okay, who's writing? Okay, now we will determine first the V sub R. So the V sub R computation is based on our stoichiometric equation. So V sub R is to 3 while V sub A is to 1. Where did you get that, miss? It's taken from here. Okay, 3 for R and 1 for A for their coefficient. Then your volume at R divided by 3, or volume due to the formation of product R, is equal to, so for this one, for A, that would only 0.5 V sub O. That would only be 0.5 V sub O because the other 0.5 is the inert. So it's not to be accounted for in here. So then we have V sub R being equal to 1.5 V sub O. Using this formula, your total volume at 100% conversion would then be 0.5 V sub O plus 1.5 V sub O, which is 2.0 V sub O. Now, knowing this, you go back here and substitute. So you have 2.0 V sub O minus V sub O over V sub O. So that would be 1, right? V sub O over V sub O, that would be 1. So that's your epsilon A, which is 1. So if you've ignored it, then it would really matter in your answer because your epsilon A in this case is not 0, but now 1. Now, since you already know the epsilon A, I'd like to go back to our given. So you'd be given a sense of direction. What would be the next step that you're going to do? Okay, this is your given information, rather this is your given information, and this is required. We already determined the epsilon A. What do you think would be the next step? So I'll go back here, have another one here. What do we do? For a PFR, what's your performance equation for a PFR? PFR equation? Anyone? Your V over V sub O, which is actually your space-time, is equal to PFR. So we now integrate. We're used to not integrating, but now there's a need for us to integrate. What is it that we need to integrate? Integral performance equation. Is this the performance equation for a PFR? Same thing for a batch reactor. Hmm? If it's an MFR, you only get this one. And you have CAO DXA, CAO XA over rate. If it's a batch reactor, if it's a PFR, this is your performance equation. Now, I'll stop sharing here. I'll show you something so you can recall. Batch plug flow. Where's the plug flow? I'll show to you the plug flow reactor performance equation. Here. Share. See this? This is part of the slide that we're now discussing the problem. So tau over CAO, that would be your V, capital V over V sub O. The CAO was written here. I wrote it as written here, but you can place it here because anyhow, it's a constant. So that would leave you to integrate the DXA RA part. Okay? So that's the one that I have shown to you a while ago. So I'll go back to our whiteboard so you can recall. So that's our performance equation for our plug flow reactor. Now, if you will follow the suggestion, that way we will not have to deal with constants in this side. So you will have here dxa over the rate. This is 0 to xa. Okay? Now, the V here, remember that the V that you will have here will now be expressed in terms of, so if this is the original equation that you have for the performance equation for a plug flow reactor, the volume that you have here must be changed to this one. So the V is equal to V sub O, 1 plus epsilon A XA, right? Though this is your performance equation for a plug flow reactor, but since we cannot ignore density changes here, so you will have to change the V to this particular format. So in here, I would write V sub O, 1 plus epsilon A XA. Okay, that's your entire V divided by CAO VO. Okay, this is only the V, but the tau is V over VO. So the VO I placed here, and you still have the expression here, dxa over the rate, okay, from 0 to xa. And since this one is a function of conversion, you have no choice but to transfer it here on the right side. So you will have VO over CAO V sub O, small v sub O, now being equal to the integral of dxa. Now your rate in this particular problem, your rate expression is this one, 0.1 Ca raised to 0.5, okay? I'll go. So this is 0.1, 0.01 rather, raised to Ca raised to 0.5 to be multiplied to 1 plus epsilon A XA. Okay? Now again, you will have a problem with Ca raised to 0.5, but no problem because you can convert it in terms of epsilon A and XA. So let's have another one here, another slide. So you have VO over CAO VO is equal to the integral of dxa. Now you have 0.01 and your Ca will be CAO raised to 0.5, 1 minus XA raised to 0.5 all over 1 plus epsilon A XA raised to 0.5. Everything is raised to 0.5 because this is your Ca now when you need to account for fractional change in the volume or expansion factor. So in that case, you have that now, and you will have here 1 plus epsilon A XA, the one that we had here. Okay, this one. So to simplify, so you could see that this one will get to cancel with this and you are left with 0.5 here. This one will get to cancel and you still have here 0.5. The resulting expression would be capital V sub O, the initial volume, CaO raised to zero point 0.5 volumetric flow rate times. So this one goes up, rather wait, zero point 0.5 here. So you have another zero point 0.5 here, and this is zero point 0.5 here. So you have this 0.01 here, I'll place in here, 0.01. Did I make a mistake in the rate expression? Wait class ha. This goes here. So multiply. So you have dxa over, I'll place the constant here. It seems like if I will cancel now, this one with this, 0.5. I still have 0.5 here. So this would be 1 minus xa raised to 0.5, 1 plus epsilon a xa raised to 0.5. This is your resulting integral. This will be integrated from 0 to, how much is our, this is actually the one that is being asked. Let me check. What is being asked is the space-time. So the conversion is 80%. So this is up to 0.8. Okay? It's already 2:32 class and I have an integral calculus class at 2:30. So I've used up your time. I've used up their time as well. So please recheck the process here. We will go back on this on Monday next week because we won't have class on Wednesday. The school already declared it as a holiday. Okay, so if I have time, I will finish the recording of this to finish the solution of this part. Okay, so I will stop sharing here and I will have to say bye for now because I'm late already in the next class. Okay, class, just communicate to the GC should you have any questions. Bye.
Thank you, Miss.
Okay.